Randomization is an important feature of many experimental processes. There are good reasons for why one might want to randomize one's experiment, and I'll explain why. But there are also some inflated claims and expectations about what randomization can achieve, and I'll try to debunk these. So, what is randomization? In your experiment, you'll start with a sample of the objects you want to intervene on. These might be a set of the same kind of chemical substance, bacteria culture, material sample, patient, school class, or anything else you want to investigate. Before you perform your intervention on these objects, you want to make sure that you have a proper comparison. A subset of the sample that is identical to the one that you intervened on, minus the intervention. That's why you divide your sample into treatment and control group. But how do you divide your sample? Do you put the most promising cases in the treatment group and the not so promising one in the control group? Randomization offers a different and more systematic answer. You use a random process to assign the sampled objects to either treatment or control. You can do this by flipping a coin or using a lottery machine or a computer. Furthermore, you conceal the assignment so that neither the experimental subjects, if you're experimenting with animals or humans, nor the experimenter knows who is in the treatment and who is in the control group. Experiments that are set up this way are called randomized controlled trials. Randomized controlled trials have acquired a very high methodological status. Particularly in medicine, many scientific organizations consider RCTs, or systematic reviews of RCTs, to be the highest quality evidence available. In so-called evidential hierarchies, some have tried to distinguish evidence by the processes through which they are produced. RCTs are ranked higher than other so-called quasi-experiments because they include randomization. In extreme cases, this hierarchy has led researchers to focus only on RCT evidence and disregard lower-ranked evidence if these types of evidence conflict. Such a hierarchization of evidence requires justification. So what are the arguments for taking randomization so seriously? There are at least 3 good reasons for why one might want to randomize one's experiment. The first is that it helps eliminate selection bias. If the experimenter performs the division herself, she might, intentionally or not, assign those particularly responsive to the treatment group and those less responsive to the control. This would threaten the internal validity of conclusions from the experiment. Randomization replaces the experimenter's influence and thus prevents such a bias. Even if there is no threat of selection bias, say because the experimenter has used another assignment process that eliminates her influence, randomization might still be a good idea, because it might help the experimenter to convince others that the treatment-control division wasn't rigged. Finally, randomization is a useful instrument to realize blinding. For these 3 reasons, it is typically a good idea to randomize experiments, in particular because randomization typically does not cause any harm. However, although randomization is helpful in these ways, there are other practices that can perform equally well. Other assignment procedures will also prevent selection bias, can also convince others that the experimenter had no undue influence, and of course there are many other blinding strategies. Thus, although a helpful instrument, randomization isn't a necessary practice for any of these objectives. Now, let's turn to a claim that is sometimes heard in support of RCTs, although it is incorrect. Namely, that randomization ensures that background factors are equally distributed in treatment and control groups. If this were true, then you would not have to worry about controlling background factors anymore. You would just randomize and the job is done. Consider this example. We have a sample of objects, let's say bacterial cultures, with different pH values. We suspect that the pH value influences the effect of our experimental intervention, so we need to control for it. Assume we know that pH values in the sample are normally distributed around 7. So the claim goes, if we randomly assign the bacterial cultures to treatment and control, then we will get identical normal distributions of pH value in the treatment and in the control as well. But is this really true? The short answer is no. Let me explain why this is at the hand of an analogy to rolling a die. If we roll a die a very large number of times, we will converge to a distribution in which each face comes up an equal number of times, and the average score count will be 3.5, as you see here in the graph. However, for any particular sequence of die rolls, this long-term distributional property does not hold. When, for example, rolling the die 10 times, we should not be too surprised with this result, with 6s showing up more often than other faces and an average score being 5. The same holds for any particular randomization. We should not be surprised that at least sometimes a randomization yields control and treatment groups in which the mean pH value differs substantially. In fact, any particular randomization might yield such differing distribution. The above claim is true only for infinite sequences, but experimenters typically randomize only once and certainly not infinitely many times. Ronald Fisher, who strongly argued in favor of RCTs, was nevertheless aware of this problem and warned that in practice experimenters will find the distribution to differ widely. So we must conclude that this claim about RCTs is false. They do not guarantee equal distributions of background factors in control and treatment groups. Experimenters are of course aware of this and therefore check for such imbalances once a randomization has been performed. For example, if they find pH values to differ substantially between treatment and control after randomization, then they'll randomize again. Alternatively, because they're now using their background knowledge about potentially disturbing factors anyway, they can also control for these factors before randomization. For example, they might divide the sample into subsamples with particular pH values, and then randomly assign objects from each of these subsamples to either treatment or control group. What is clear, however, is that these strategies can only be applied to correct for imbalances of known factors. Yet these imbalances will also arise for unknown factors. But because they are unknown, one cannot correct for those. Thus, randomization cannot guarantee the control of unknown factors. Another problem that arises with RCTs, as with other experiments, is that we cannot simply apply the RCT result to some other situation. RCTs give us an average treatment effect as a result, the difference in mean outcome between treatment and control group for that sample. The sample is of course drawn from a larger group of objects, which might be called the population, although this larger group is typically not well defined. But we cannot simply apply our RCT result to another sample drawn from this population because randomization is not the same as random sampling from the population. In medicine, for example, the sample of patients is typically constituted by those who at a given time walk into the hospital and exhibit the relevant kind of symptoms. It might be in principle possible to perform a sampling process that is representative, but randomization itself does not ensure that. Consequently, we cannot simply transfer our RCT results to other situations unless we argue that those situations are relevantly similar to the ones under which we performed the RCT. Such a similarity judgment, however, requires background knowledge. Again, pointing merely to the process of randomization does not provide justification. To conclude, there are good reasons for why one might want to randomize one's experiment. However, randomizing is not necessary for those objectives. Other practices can perform this help too. The importance of RCT is also sometimes exaggerated. In particular, randomization is not a guarantee for control of known or unknown background factors, and RCT results cannot be generalized without further argument. In order to deal with these problems, one needs to refer to background knowledge and cannot rely solely on the procedural feature of randomization itself. In the light of these arguments, it is not justified to consider RCTs to be in principle better evidence than other experiments.